Say record. All right, we're ready for you.
Hi, my name is Sheila Mongi, and I go to Bergen County Technical High School.
My name is Bridget Liu, and I also go to Bergen County Technical High School, and we're both in the aerospace engineering division.
And
Terrific.
our project is additive manufacturing.
So some background on, first of all, what is additive manufacturing even mean?
So basically, when we were getting the gist of our problem, we wanted to get like the background and the objective. So our objective is to make a 3D printed tarp stake that can be used to stake like a tarp onto the moon, like the surface of the moon, so that the astronauts will minimize the amount of dust that they are exposed to, for them to walk on during their time on the moon.
And some of our like key points we'll be going over is the criteria. So what does the tarp stake need to accomplish? Some of the constraints of what we want the tarp stake to satisfy. And then we look at some existing tarp stake designs and we use that to develop our tarp stake prototype. And then we'll discuss some things to consider related to fitting a tarp stake that's used on the moon. So the criteria for our tarp stake is it needs to have an attachment to a drill. It needs to have a cable attachment, and it has to be able to be used by astronauts. So that means taking into consideration that they'll have limited hand mobility since they're wearing the spacesuit, and also limited overall mobility. And it also must be a maximum of 6 inches in length.
As for our constraints, we may mainly focus on the fact that it cannot be a trip hazard. We want to not be able to create an excessive amount of waste since this is going to be printed on the moon with the aluminum that they're able to find there. And we also want to have a balance between durability, hold strength, and the force that is needed to pull the stake actually out of the regolith. Also for the materials used, when we're 3D printing, we're going to use PLA, but the final product will be made out of aluminum from the moon.
Okay, so to start our design process, we looked at a lot of pre-existing tarp designs, mostly like the common commercially available tarps. And based on like looking at a lot of reviews and analyses of tarp designs and shapes, we found that the Y-shaped tarp was the most strong and resistant to bending. So that was the shape we decided to start with for our tarp prototype.
So now we're going to get into like our actual design evolution. So our first design, we wanted to start with like a basic Y tarp shape. So we started by drawing just like a sketch of like what we were going to have the tarp actually look like for the actual just the tarp in general, not with any of the attachments. So with that, I went in and I 3D modeled like what that would look like, which actually took a lot of time because I had to consider how to like make a plane that would slice off the top of the tarp stake so that we'd actually have an angled point that would be able to drive into the regolith easier. But some of the things that we found with this tarp stake, the base one that we use, in regards to the criteria, it was fine for the length and for the trip hazard since there was actually literally no attachments attached to it, so there was no like risk for a trip hazard. But for the ease of use, we found that like due to its small size and its lack of a base or any attachment for handling, it would be considerably hard for the astronauts to actually use this with their limited dexterity. So that was something that we considered when we were actually going to move forward with an actual design. Also for the strength and durability wise, we found that like it was very easily bendable, but that might have just been because it was actually printed out in PLA rather than actual aluminum. But we still wanted to make it a little more durable and a little thicker so that we wouldn't have that problem if the aluminum was like a little similar to the PLA that we're using. But for the weight and the materials, it was actually very lightweight for our actual tarp stake design, and it was very material efficient so that we wouldn't waste material on like the infill or the support needed to actually 3D print it.
So for our second tarp stake design, we started thinking about how we would incorporate the attachments that were part of the criteria. So that was a cable attachment, an attachment for a drill. So we looked at how some other tarp stakes had those attachments, and we sort of came up with our design where we had a piece on top that had a hook, and that would be the cable attachment. And then the hook also connects, or it would be screwed into a piece that's connected to the tarp stake. That would be the attachment for the drill. So we thought it sort of could be, so it would be in two pieces, but since the cable attachment was removable, once it's in the ground and the sort of cable attachment is removed, it could still be flat to the ground. And we printed our design, and we found that the hook part needed to be made a lot thicker, because in our current design you could see it's the orange. The hook came off pretty easily. So we're also thinking about doing one-piece designs. So that brings us to, oh, and before that, but for tarp stake 2, the alignment to criteria was, we designed it so that the including the attachments from top to bottom, it would be 6 inches. And then for ease of use, we originally went with the screw design where the cable attachment screws into the tarp stake that has the drill attachment. But considering the hand mobility with the astronaut spacesuits, we are thinking about reconsidering that design. And then for the tripping hazard, with the cable attachment, it would pose somewhat of a trip hazard. But if you were to take it out, it'd be more of a flat surface when screwed into the ground. And then for strength, we mentioned the issues with the hook needing to be a lot thicker in order to prevent coming off easily, but that might also be because of the PLA material, and it might not be as much of an issue with the aluminum. And then the materials on weight was still a pretty good ratio, since our inside was hollow. And then for things we're considering, we were gonna increase the thickness of the cable ring and redesign to have it maybe be one piece and have the attachments be all part of the stake design. And then also change the way the removable cable attachment is implemented.
So for our now current prototype, we're trying to go more outside of the box. And we have like a little design over here that would include little holes within the actual stake itself, which would minimize the material that we actually need in order to print the actual stake out. So that would help with the lightweight material. But also we want to have the cable attachment be attached to the side rather than the top. So that it would pose less of a trip hazard, and we maybe have more leeway with the way that the drill attachment would be implemented.
And then we get into our considerations for specifically designing a tarp that's going to be used on the moon. The first consideration would be particulate matter. So since the moon's regolith is made of a sort of like chalky material, putting like a stake into it and taking stake out would generate a lot of particulate matter, which can cause a lot of health problems for astronauts, as well as damaging machinery or other technology if it were to come into contact with it. So our goal is to generate as minimal particulate matter in the process of using our stake as possible. So in order to do that, we're thinking about like different designs in our stake. For example, we are thinking about a design where it sort of like has holes in the tarp stake that will like sort of cling onto the moon's regolith when you insert it and take it out. And we are thinking that might help with the minimizing dust particles issue.
Our next consideration was the astronauts' physical capabilities, because we know once astronauts actually get into space, their physical capabilities start to dwindle pretty quickly. So we're focusing on like the impacts on human physiology and how in space, there's a lot of swelling that goes on actually within the human body because of the different forces that are being applied and not applied. And also with their pressurized gloves that limit their hand mobility, we want to ensure that our actual design, if when it's finally complete, will be able to be used by those astronauts while they are actually while in their pressurized suits to be able to both put it into the actual ground and also take it out of the ground. So for our design consideration, make the average we're trying to have the pull force needed to remove the stake be at or like a little below the average human pulling force so that these astronauts will still be able to pull the stakes out when needed while they are on the moon for the whole entire time that they are on the moon.
And then for testing, so our testing process is going to be, we already have the quick read dry concrete mix that's gonna be used to simulate the moon's regolith, and then we're gonna be inserting our stake in and then pulling it at different angles, like a 90-degree angle, 45-degree angle, 30-degree angle, using the guide wire, and we're gonna be seeing like the amount of force it takes to pull it out. And then we're also going to be testing at different angles to see how the force varies and try and optimize the angle.
Okay, good job, ladies. Tell me about so looks like you've tried one particular stake, and it looks like one that I could drive in as well as use a drill to drive it in. Does that sound right?
Yeah.
Had you looked at anything with threads on it? Because so that as you drill it in, it would it would help pull itself in.
We actually did consider that when we were first looking at the different types of tarp stakes that there were. But with how like we were looking, because we made a pew chart on the different categories that would be considered for those. And for the one with the threads, we found that it wouldn't be as great because it's not as durable in like those harsher conditions, which we would face on the moon. So that's why we didn't consider it originally, but we're still trying to figure out how we could probably implement those threads because it would make it sort of easier, especially for the drill.
Yeah, I think we what we found is that you take a let's see, because of the way the regolith is compacted, so you can all of the little particles are jagged, and so they kind of cling to each other. And when you hammer it in, you'll hit it a couple of times, and it'll seem like it's going down. But then the astronauts found that as soon as they got to like after 2 or 3 hits, they couldn't get it to go any deeper. And so the only way that we're going to be able to get this in is to drill it. And then if you think about it in terms of those threads, every thread that's holding dirt on it is also holding the stake down more. So the weight of the dirt is actually what's holding it down in some cases. And so being able to have some good threads on there is going to be part of what's going to make it a really good stake. Does that make sense?
Yeah.
Okay. Now the hard part with that is that it's hard to 3D print those without having a bunch of support material.
Yeah.
And that's going to be the hard part about it. So, yeah, those are some of the things you've got to think about as you're going. Okay. Good job, team. Go up a couple of slides, could you? Okay. Go back to that last idea you had there. There, that's the one. Tell me a little bit more about that device that's down at the bottom. What were you thinking there?
That device actually was on one of the slides that was a part of the additive manufacturing presentations that we were given. And when we were looking at that one, we found that we were just interested in the way that the dirt would cling inside the actual tarp stick itself, which would help it actually stay within the ground more. That is what we were originally thinking with that idea. And also with it being hollow, it would make it more lightweight, which is something that we also wanted to have prioritized in our design.
Excellent. So I think that there's something interesting to be done there. And of course, that's got a blunt end, so it would make it hard to kind of jam it in the ground. But there might be some other ways to get that to go in better. But the idea of, having that open space there, I think is a smart idea. And I like what you've done by suggesting putting the tether point on the side of it, making it less of a toe jam. I think that's really smart, ladies. Good idea.
Thank you.
Thank you.
Okay. Go up another slide for me. There. Go back to the printout that you've got there. Another slide. Now go down. There you go. Okay. And I like what you've done here. So this is that Y shape. Is that correct?
Yeah.
Okay. And I think that's really smart. These work well in sand, but I don't think they're going to work for our case as well. But I'm glad you did some good testing on that. It sounds like you've already done some good work with that. Excellent job, ladies.
Thank you.
Flo, did you have any comments for him?
Your PowerPoint is awesome. You've done a really nice professional job there. And I actually think this project has what I would call three variables, okay? Because you are using eventually the aluminum on the moon, hopefully. All right. So, one thing that will add more use of aluminum is the infill. So the infill, you have to, it's a variable, how much you use. The scaffolding is the other variable on how much material you use. And the third variable is in your design and how much you use. And those three things have to, you've got to figure out a sweet spot where those three things combined are able for you to produce the strongest possible one that will go through the regolith on the moon.
Okay, so Flo's there and Glenn's there.
Yeah, and Stacy Hill is here too. He's the founder of the HUNCH program. And
Yeah,
go ahead, Stacy.
So looking at this one, which is a Y-shaped, it would be interesting if you could push that down in the ground and then put something down the center that would spread the end, right? Kind of like a drywall hanger.
Yeah.
Which I never really thought about before, but and I have some ideas of how you could do that, but I'll let y'all try to think about that.
That would be interesting. And just this morning, my husband was online talking to the Dow space farmers in Michigan for an hour. And he was talking about the different probes they use to get soil samples, right? He's a soil scientist. And he said to not disturb the soil. And that's what you were talking about. You didn't want to disturb the dust a lot when you were designing something. He said to not disturb the soil, they would have a probe that they would just push down. They also had probes that were hooked up to the truck they took out on the field that actually drilled down because there were rocks. And that's the kind of situation that you will probably find in the regolith on the moon. But I like that you were really interested in not causing all this dust flying up and causing a disturbance, because eventually we will want to see what actually is that regolith, and take some soil samples of what we're dealing with when we go to the moon or to Mars or beyond. So that was really good thinking on your part. I really like that too. All right. So
good job, ladies.
Yeah. Who's Jonathan? Is that another team?
Yes, very good.
Yeah, that was really nice presentation. Stacy, they're in New Jersey, right outside of New York City, actually. And I did get to visit them when I was in New Jersey this time.
Oh, good.
Yeah,
Very good.
it was awesome. All
I
right, so
plan on
then,
going to your Rutgers CDR.
oh, awesome. Well, they're coming too, so you'll get to see their project. But if
Good
you have
deal.
any questions, you can always email me. Just copy your teacher so I know what team it is. So that's great. All right. So the next team is going to be a camper team from and it is Bergen County, um, Bergen County Technical School in Teterboro, New Jersey. Good afternoon, everyone. I want you to introduce yourselves. This is the first year the school is participating. So introduce yourselves and then tell us about your camper for the moon.
I'm Jake Berg.
I'm Do-Yoon Jim.
My name's Aiden Hyun. And
Our project was at NASA HUNCH Lunar Camper Lab, as you said. Yeah. There we go.
okay, so we had an initial prototype creation. So we initially thought of a scissor lift design. So because the lunar camper can only fit in a 2 meter by 1.5 meter by 1.5 meter,
Yeah.
we have to expand it when we get there to actually fit everything we need for the design. So we were initially thinking like something similar to a scissor lift. So our initial prototype creation, the two pictures on the top, we made the scissor lift out of popsicle sticks and toothpicks. So the left picture is when it was folded and the right picture is when it was expanded. So we were able to get like significant like height out of the scissor lift. So we were planning to integrate that into the camper system. And we also started a 3D model for the scissor lift on Onshape. But as we were doing the scissor lift design, we realized that there were like too many fail points on the scissor lift because every single hinge on the scissor lift would cause like a tension point. Like if one fails, it will cause the entire design to fail. So we decided to go on to a different design instead of using the scissor lift.
So some inspiration we got was from the NASA Beam project. The Beam project includes like an inflatable I guess pod that was attached to ISS. The constraints are around like 7 feet collapse and expanded over 13 feet. So like this is kind of ideal for us. It's made of like a similar Kevlar, which is also able to withstand the moon environments. This is important to us because it allows us to expand without having many fail points. There's only expansion and it's basically just based off a torque.
Okay, so before our expansion idea, we had this a bit of prototype for expanding our base, and it was this little box here that I have in my hand. Is also in the photo. Oh yeah, basically the sides just expand outwards, and it grows into like twice its size. First it goes sideways, and then it goes up. And like this is our initial like small prototype.
Mhm.
And it was able to give us a significant amount of space compared to the original size of the box.
Can you do that again? That was really cool.
Uh,
You're on camera, you're on camera.
oh, sorry. So this is the expanded version. It's
Okay.
it might not be as big in model size, but in reality, gets this much.
Very good.
So yeah, we thought of this as like a starting point, I guess. Just a checkpoint to hit. And I know this is like kind of flimsy. It's like a bunch of tape and cardboard glued together. But the tape might represent the expanded mechanism we're working on. And we're still finalizing that, but we think of many concepts of it, as Ada mentioned. But we'll finalize that pretty soon. And we're also trying to connect this with other ideas that I'll mention in a bit. So yeah.
Okay, so this was our second design after the box design that Doyun just showed you. So before the design is we wanted to make the beams be like the expanding part instead of like the entire room. So like we were thinking like it's not shown in the picture because we didn't really have enough time to create it. But the floor would be made of like some expandable fabric that's like durable on the moon so that only the beams would be expanding. So I, but we made another model like here. So this one doesn't have like the floor in the middle. It only has the beams. So it'll expand out like to on the base and then it would go up. But think we also like made the top go up and I don't have enough hands to actually show you. So we also have that design that we made. So we were thinking like maybe on the beams we have like rolling tracks to expand or pistons because we only need to fold it. We only need to bring it out once, but we don't. So I think where is it?
It's in the middle.
The thing?
Yeah.
So we were thinking like a piston like
If you
here.
could
So
stop sharing, we might be able to see that a little bit better.
Yeah.
There you go. Okay.
So this piston thing, so this is like the beam and this is like the part where it expands. So as when we get there, we would have like a spring mechanism-ish or a piston mechanism that like we expand out that it expands out when we get to the moon because we don't have to bring it back in again. That was like our second design.
Okay. Very good.
So I mentioned earlier that there were other ideas that we're trying to combine with it. So the beam that Jake mentioned earlier, we really like the idea of an expanding like balloon type of idea. So I initially created this paper balloon out of material provided, and it's just a simple origami trick I learned earlier. But it's deflatable, and I thought it could be like a another checkpoint for like how we could start on this expanding idea. And so we are given this like small base dimensions to start with. So we were thinking of expanding this balloon from the actual box itself. So yeah, I know. So this would be the like just like a kind of a small example, but like um basically the opening of this balloon would connect to one of the openings of this box, and it could also fold inwards like that. And inflate outwards from a mechanism that we'll figure it out. Like there's many that we could think of, like oxygen, or just pressurized chambers. But yeah, we're trying to implement these ideas together, as you can see. And
I
at
think
first,
I really like your last idea there, just because you're using a combination of the rigid box as well as your inflatable idea, and that's
Mhm.
similar to how NASA does it too, or some of these other companies. So I think there's a lot of value to that. Now, one thing I wanted to mention to you is that, you know, so we've got this box that's 1.5 meters by 1.5 meters by 2, and what's interesting is you can have, this might be your one. Um, so this is my 1.5, and then this might be my 1.5. And then you can put your two straight up. So you can change the arrangement so that it's 1.5 can be down, or you can have the 1.5 up. So you can expand it in different directions,
yeah,
but you may not need to expand it in the vertical direction if you want. Does that make
yeah,
sense?
yeah. We were thinking of ideas like just to make like sometimes to just even think of the box as an entrance to the actual base and having the balloon be the main base as it expands outwards. So in that case, we could just honestly just keep the box the same size and just have it vertically so that the 2 meter side would be on top so that the astronauts could just fit through as like a door mechanism kind of. Yeah. And
I think that's great.
yeah, that was
And
one of our ideas.
and
Um,
have you been thinking? Does this is this going to be a trailer that's pulled, or is it going to go on the back of the LTV?
yeah, it'll probably be a trailer.
That's
Just to have
fine.
like a base for the actual main base to go expand outwards into.
Sure.
Um,
And then
yeah.
have you started thinking about how those wheels are going to fit in there as well?
Um,
So there was one idea where we have like the wheels inside like the main like body, and then when we get to the moon, the wheels will just like pop out downward, like basically like a plane's landing gear. So that if it when it pops out, it'll just like stay on the ground, and we won't really have to expand it, put it back in again.
I think that works. And yeah, you've got the advantage that you only have to set it up once and you don't have to take it down. So I think that's great. Now, consider how big do these wheels have to be? If we're talking about 1/6 gravity and we're not trying to drive the wheels, we're just pulling the wheels, right? Do they need to be wide, or can they be narrow, more like bicycle wheels or something like that? And so these are things I want you to think about in terms of how big do they need to be, because that helps you with your dimensions as well.
And when you're thinking about that, I don't want you to worry about the wheels on the lunar rover, okay? Because that hasn't even been made yet. So don't worry. Sometimes people ask, well, what are the wheels like on the rover? But we don't know really yet. Is that right,
Well,
Glenn?
that's right, and it doesn't matter because this is a separate vehicle from that. So all you need to be thinking about is what is their task, um, and how big do they need to be for what you're doing. Okay,
Mhm.
good job, team. I like what you're doing. Do you have more things to tell us about?
that's it. Yeah.
Oh,
Okay, excellent job, guys. I like what you're doing. I think you're going on a great path. Also, so was that an origami box that you were inflating? Is that correct?
stop
Yeah, no,
stop sharing so we can see that up close. That's okay. Thank you.
so the idea here was that it starts as this small little box. I made three sides of it first so that we have a base to start off of, like one, two, three. And then I made another, like there was many parts to this box. Like I would say like almost some parts of it have like 4 layers to it. But that would allow for like multi-layer expansion so that the under layer here expands outwards. Almost like you could think of it as like a rolling mechanism. Like there could be wheels under here that's rolling this compartment outwards. And then
Sure.
there's another compartment up here that rolls outwards, upwards actually. So then the initial expansion could look like this, just a
Right.
little bit, right? And then to the side, like that. So then
And so
ends
I I think that's really cool. Um, there's some real value to that. The difficulty is keeping it sealed when you have sliding things like that.
Yeah, we were having some ideas about how we could keep it sealed. One idea we were just kind of thinking about was of some sort of fabric layer
Uh-huh.
encasing the entire box. That could expand outwards with it as well, and just its whole purpose would be just to keep it airtight and protect it
Sure.
from maybe like moon dust or anything.
Now, and then show me the other one.
So this
The
one,
inflatable, the
The
inflatable.
oh,
the
this one,
inflatable one. Yeah, how
So
did that one work?
this one was initially just a little origami balloon. I kind of ruined it because I was trying to think of a different idea, and trying to like improve it in a way. Because the initial balloon, its only way of deflating was just folding it inwards, and that left like a very flat surface, and it was too big to even like really fit in the box. So we were thinking of some, like kind of those child toy tubes that people crawl in. Yeah,
Yep,
like so they actually fold inwards like this, right? So
that's right.
that's the idea we were going for, and it's similar to the beam. Yeah, it's like kind of like a lantern, yes, but
Yeah, I think
essentially, yeah,
I think there's some really good idea with that. I like what you're doing with it.
yeah. So we were trying to make it fold inwards rather than like sideways and like keeping it a flat surface, so that it would actually just be like right into the box like that. Almost like an accordion, I guess. But
Yeah,
it would expand in a way. So that's the idea we're going for, and we're probably going to think about some other ways because this is a bit sloppy. We'll finalize the idea pretty soon, and
Okay.
hopefully that'll connect well.
Very good, team. Excellent job.
Let me see your frame structure.
He wants to see your frame structure. The box again.
This one or
Not the box, the frame.
Not the box, the frame with
This
the
one?
beams. Yeah.
The beams, yeah.
So this one is similar to the box, but we only the beams expand out. So this was outside, it would expand this way and it's like this.
Right.
And
So
you
I'd
go
encourage you
projection
to design the beams in such that each corner is designed the same way. All right. So what I mean is that right. So basically you could think of this as having an X, a Y, and a Z beam. Does that make sense to y'all?
Yeah.
So each X would be the outside, each Y would be the inside, and your verticals then would then alternate. And I assume you have another set that would go on top of that. That would be going
Yes.
downward, right? So
Yeah.
so create them all the same, except for those on top would be the inside and those on the bottom would be the outside. Does that make sense?
Yes.
Right. And then you could also have something in place that would like snap out and lock it open. So it's a one-time thing that once you pop it out, it's out.
Yeah. So we were actually thinking of like a small piston mechanism. So like when it comes out, like a piston would like spring out from maybe like a spring, and it would lock it in place so it won't move anymore on the sides.
Okay. And then, all right. So a piston is a little bit more challenging, I think. Try to simplify.
Yeah, we're gonna think of how to combine ideas in the most efficient way, I guess.
Sure.
So far
No,
this
absolutely. But good thinking. I like your ideas.
Yeah. And I have to show you this. So this is actually from Japan, and it's an origami balloon. It has a little opening I can blow into it, and this is over 30 years old. But it still holds air, and it's really cool, and it collapses just like does a really good job of doing it. It's just got a little opening for that. It was given to my son
Is
by
is that made out of paper?
it is a paper.
Wow, that's interesting.
And it's really old.
Mm.
But it's lasted. I just love this. It's a great idea. I love what you're doing, guys. That's really a cool combination of things. So keep it up.
Thank you.
And there's the collapse ball.
Good job, team. Keep this up.
Yeah,
Thanks.
awesome. And Glenn and Stacy, thank you for your comments. That's awesome.
Yeah.
All right, so now we're going to go to, thank you, team. Have a great afternoon. So now we're going to, the cosmic dust collector.
Excellent.
Hello.
Oh, and this is my team of young ladies. I remember talking to you a lot.
Yes.
So let's see what you have. Introduce yourselves.
Hi, my name is Georgina.
My name's Molly.
I'm Emma, and we're doing the Cosmic Dust Collector project. We just have to pull up our slides. Yeah, we're just pulling it up right now.
Sure. Right here. Okay. And then full screen it.
Slideshow. Do it. Slideshow. You see where it says
Yeah.
slideshow?
Flipping over. Yeah. Do you see that?
It's coming up. It's coming up. It's loading, it says.
Okay.
We don't see it yet.
Uh-oh.
Oh, it says your screen sharing's paused. Hold on.
Uh-oh. Sorry about that.
That's okay.
Oh, resume. Press resume. Sorry, our teacher's
Sorry.
gonna come and help us real quick. Technical difficulty.
My screen sharing is paused, but then when we click resume, it doesn't resume.
Let's go back to your slideshow.
It's in Safari.
Let's keep that up full screen there.
think it's going to a different screen, so click on
This is the little arrow, right?
click on the arrow, yeah.
Presenter view.
You know what, you might have to just do it like that where it's not full screen, because it's for whatever reason, it's taking over to a different screen when you go through this social view.
Okay, thank you. We're gonna try it this way. We may not be able to
Make it into a slideshow. That's okay. We see it pretty well.
I can see it fine.
Yeah.
Well, my name is Georgina, as I said before.
My name's Molly.
My name's Emma, and this is our preliminary design review for the Cosmic Dust Collector project. So first, throughout this design process, we've been considering the criteria and constraints. So first, our project has to be simple because it has to be easily repaired if it were to break. It also has to be easy to use because it's going to be used by astronauts and they have bulky gloves on. And number 3, it has to be airtight so that contaminants don't get into the dust when it's taken back to the ISS. And number 4, it has to be lightweight because it has to be shipped to and from the International Space Station. And it has to be able to withstand extreme temperatures in space.
So after reviewing our criteria and constraints, we did some research on cosmic dust so we could better understand what it is we're doing. Cosmic dust is made up of interplanetary dust particles, which are made from comets and other space debris. And it's important to understand them because we'd like to know as much as we can about our universe, and we'd like to know where they came from and what we could do with that. So they've been largely studied in the form of micrometeorites, which have burned up a bit in the Earth's atmosphere. We'd like to study them in their purer form out on the ISS in space before they've burned up at all. So NASA's Cosmic Dust Collections has over 11,000 particles to date, and they've been collected through 2 main methods of South Pole water well collection, which has collected micrometeorites as they've fallen from rain onto the South Pole and frozen into the surface. They've been drilled up and the water's been evaporated to reveal the micrometeorites, which have been studied and collected. And we took more inspiration from the aircraft collected particles, which were collected on sticky plates in high altitude planes, which were sent into low Earth orbit, and the sticky plates picked up the dust as they flew past and brought back to Earth to study. So we liked the idea of the sticky plates, and we also liked the idea of shipping with silicone oil, which is the high viscosity oil that traps the particles and doesn't allow any other contaminants to reach them.
So moving on to our next stop, we wanted to share some of our initial brainstorming. In this, we kind of just put like any ideas that we had to paper and just kind of wanted to see what we could come up with before we really took into consideration the criteria and constraints. One thing that we did come across that was really important was biomimicry, where we would take an aspect of nature and kind of engineer something similar to that as a means of collecting the dust. So we found bees and their method of pollination, and we kind of used that. So this kind of transformed, once we finished the initial brainstorming, we took our criteria constraints and moved on to a more narrowed down solution. So our first concrete idea was we called the sticky plate grabbing arm. It had 2 arms, and the arms had suction cups that hold glass slides, and you could easily be able to take the glass slides that had the dust on it and put it into a microscope for observation. And we thought it was the most simple, but it was the least unique out of all of our ideas. So moving on to our next design was the magnet with the gloves with a magnet on it. These were the astronaut gloves that were able to kind of pick up sticky slides and then manually press them against the ISS. So it would be a simple way of kind of collecting the dust. But some of the negative aspects of this design was that it was kind of hard to also have a container on the side that the astronauts would have to deal with. So it was complicated because there were a lot of different components. Yeah.
The other design that we looked over in this phase was our fuzzy barrel design, which used aspects of biomimicry to have a fuzzy barrel picking up dust as it spins along the ISS. It would use a hand crank, and the dust would be combed off of the fuzzy part and into a container, which would then have to be sealed to be airtight. What we liked about this is that there was no contamination from any sticky oils or anything like that. But what we didn't like about it is that it's the least simple. There's the most components. It would be most likely to break. And if it did break, it would be the most complicated to repair.
So after we created our 3 designs, we used a Q chart to kind of compare these designs in when thinking about our criteria and constraints and see which one kind of did perform the best under those criteria. So we had the spacesuit, it had to be able to.
Okay, I found this on the web for so we said the space spoon.
Sorry. The spacesuit had to be easy to use within the spacesuit. It also had to be airtight and light because it is expensive to send stuff up to the ISS. Had to be simple in case it broke. And then also we kind of found in our research 5-minute EVA where astronauts would spend 5 minutes outside the ISS. It wouldn't take very long. So it would need to be a simple process and it'd have to be very individual. So after using the P chart, we determined that the plates design was our best and it kind of performed the best in comparison to our other designs in all of these categories.
So throughout this whole design process, we received like various important insights from various professionals in the industry, like Dr. Gold and an employee from L3 Harris. So the employee from L3 Harris told us about the constraint that is the 5-minute EVA. So whatever our design was, it had to be simple enough to be used in 5 minutes. And it had to be for individual use too by one astronaut. And Dr. Gold introduced us to the idea of the reusable water balloon, which can like open and close and it's magnetic. So it can be used multiple times and has a very flexible material. And we also learned from the person from L3 Harris about aerogel, which is a means of collecting cosmic dust. And aerogel is a silicone-based solid with a sponge-like structure. It's pretty much 99.8% empty space, and it traps dust particles in that empty space. And it was used on the Stardust spacecraft in 1999 to trap cosmic dust, and it worked successfully.
So after all of these researching and initial brainstorming steps, we landed upon our final solution. We have it here. It's basically a one-handed mechanism used where astronauts can kind of just push. The aerogel would be sitting right. Yeah. The aerogel would be sitting right here, and they would manually push it onto the outside of the ISS because it isn't a gel, so you need to apply some pressure. And then once you had pressed it onto the ISS, collecting the dust, you would pull this bar to close the capsule closed, and then you could kind of like use multiple ones, so it isn't just a one-time use. And yeah, this is our sketch. I don't know if that can help.
Does it any justice?
Mm-hmm.
We updated our Pew chart to show our current solution and how it fits more of the constraints than any of our other ideas. But we still have a few improvements to consider. The first being the material. We were hoping to find something temperature resistant and lightweight so that it could be used outside of the spacecraft and still be shipped up to the ISS without costing too much. But we would also like it to still fit these, it has to be rigid here on the sides and more flexible up here. We like the idea of the silicone type of material because it then, when you bring it into the pressurized environment, it would flatten out and not break, but it would still be airtight. We need to think about the size. We don't know if this is a good size because it needs to be easy to use with gloves, but we also want it to collect a maximum amount of dust. So we might make it bigger, but that would also make it heavier. So we're working on finding that sweet spot. Another thing is the analysis method. We need to research the contaminants in aerogel and make sure it's the best material to be collecting the gel. And we'd also like to look into microgravity, have some sort of wrist strap or something like that to hold this onto the astronaut as they're doing their EVA. And then one other thing that's not on the slide is we'd like a way to hold this onto the sides as it's being pressed onto the ISS to collect the dust. We were thinking magnets would be a good way to do that because it holds it on and then it could be pulled off without breaking anything. Here's some sources that we used, and
thank you for watching.
Good thoughts, ladies. Could you stop sharing so I can see your device a little bit more?
Yeah.
Mm-hmm. Okay. This right here is what we have. Yeah. I'm sorry. It's this reusable water balloon that was gifted to us by Dr. Gold. And
it has a string attached with just a little bit of slack. And these are popsicle sticks. We would have to use obviously a different material in space. And they have a little hole in the center that will pull the string through and collapse. The aerogel would be right here. So it press on, collects the dust, and then when you pull this, it would close.
Okay. That's really interesting. I like what you're doing there, ladies. It's very smart. Just as a thought, you might look at, those grabbers that you can buy for getting trash. That might be similar to what you're looking for that device, so that you're taking the pinchers off of it and you're putting the two hemispheres so that it does that. Does that make sense? And I don't have a clear picture as to how that might work, but it might give you some of the same action that you're looking for there. Is that okay?
Yeah. Yes. Thank you.
Okay.
Thank you.
Now, another thought. So the aerogel was used so that as particles were coming towards the aerogel, it's kind of like a sponge. And so they would impact and they would slide in it. It doesn't have any kind of an adhesive. So you might look for, I don't think you'll be able to use aerogel for for that location, the way you're trying to use it. But it's certainly, it's a great idea, but I think it's a different application. Now you did have some other materials that could go into those spheres and be able to do that. And so I think you guys are onto some really cool ideas here. Excellent job, team.
Thank you. So that's exactly what I heard from another team, because we did do this cosmic dust collector before, and they said that when they collected using aerogel, the cosmic dust had to be on the move. Well, now that's what the team said, that they just exposed let's say the plane that went up, but it was moving, everything was moving, and we want to collect the cosmic dust that's stationary on the ISS. So that the aerogel may not be able to collect the cosmic dust on the ISS, but it could be able to collect the cosmic dust that is moving towards the ISS.
Yeah, if we were to put it on the outside of the ISS and have cosmic any cosmic dust that was hitting it, striking it, it would capture it. But because this stuff is already stationary, I don't think it would do what we're looking for.
Okay, good to know. Thank you. Thank you.
Does that make sense? Look up about that aerogel, because I didn't know that. When the kids presented, they said, oh, it collects it nicely when the cosmic dust is coming at it, but not stationary. But there could be something else.
So part of what I really like about your design is how it's closing it in and capturing it. And I think that that's actually one of the most complicated parts of this project. It's one thing to go outside with a wipe or a piece of tape and stick it to the wall and bring it back inside. The hard part is keeping all of that protected from all the dust and things that are inside the space station. And I like your idea of how you're capturing. I think that's a really smart idea. Keep this up, ladies.
Thank you.
And
so my concern on this.
Oh, go ahead, Stacy.
Is how is that material going to respond to extreme temperatures?
Yeah, that's like what we were saying at the end, how we'd like to research materials with similar properties that would handle temperature better.
Okay, so you're currently not thinking that magnetic balloon structure will handle cold temperatures well.
No, this is a toy. This is a toy.
That's a toy that holds water, right? So the challenge is, if it starts to become less flexible, and then you bring it inside, and that thing's immediately going to collapse because it has a vacuum on the inside.
Mhm.
And when it does that, are you going to lose your seal?
Right.
Yeah. Okay, good. But good job. Very good.
Yeah,
Thank you.
it might make the seal even better. I don't know. But what I was going to say, you see that little part that you were going to use to collect the cosmic dust? Make the hinge bigger, right? You can make that any design when you're designing your
Right. But if you mount
thing.
something to that, you're going to interfere with it closing and sealing.
Yeah, well,
Right.
you got to, yeah, you got to be really careful about that because that's an important point. Yeah, absolutely, Stacy. So that there's a lot of issues, but I am sure you can figure them out.
Keep it
Do you
up.
have,
Absolutely.
Thank you.
do you have any questions for us?
Oh, yeah.
Other than our questions about the material, the size, would you say this is a good size or should we try to make it bigger?
To
Well,
me, the size thing is what are you putting inside of it? How
Right.
big is the thing you're putting inside of it to collect the dust?
well,
Okay.
it's also about surface area, right? We're trying to, so is your intention that it goes up against the wall and then it closes? Or are you going to drag it against the wall so that you're trying to pull more surface or get more surface area? And so, I guess I would, part of it is, how do you intend to use it? Is it something where you're pulling it across, or is it something where you just put it on and then you're done?
We haven't fully looked at our options yet, but that's definitely something to consider.
Okay,
Right. So what he's saying is size depends on what is your plan of use.
sure.
Right. The other question you should be asking is where's Glenn's hat?
Say that again. I'm sorry.
Why doesn't Glenn have his hat on?
Oh, because I'm at home.
Okay.
Okay. Excellent job, ladies.
Yeah, thank you so much. Keep thinking. Thank you. Have a great afternoon. Okay, bye-bye. All right, so now we're up to another additive manufacturing team.
Hi, good afternoon.
Hello.
Hi.
So we're another additive manufacturing team. My name's Saul.
My name is Brian, and today we're going to present our preliminary design review on the Lunar additive manufacturing project, which focuses on creating like a durable tarp stake that can be used efficiently in space for like more coarse like dexterity and like environments like such as like the surface of the moon. And the tarp stake is designed to secure objects on the moon and on Mars, and it can ensure like astronaut safety while ensuring mission efficiency as well.
Okay. So here's just some of the stuff we're gonna go over. So we're gonna have an introduction and obviously the problem statement and like our objectives when starting this project and the constraints we had to follow so far. And then we're gonna go through some of our designs already and how we evolve them over time and some of our research into material choices and how we're gonna test it.
And you might, Aiden, want to briefly go over those first few things because we know the statement, we know the objective, and we
Yeah.
know the constraints, but we don't know your design development.
Yeah. So we don't need to and then we're just gonna also go over like what our next steps are and what we hope to complete in the future.
Yep,
So,
that's important.
Obviously all this stuff is you know already. The other group probably went over like the design objectives and the constraints, so we could go over that very quickly.
Then here's our problem statement. I'm sure it's been addressed before, but just to double down on it, that some of the problems that are going to be addressed with the production of this lunar tarp stake are the cleanliness of like the astronauts and their suits, accessibility. We need the tarp stake to be easy to install, as probably mentioned before, and not a trip hazard, and manufacturable because we want it to be universally designed in a sense that it's easily to replicate and it minimizes the amount of material used or consumed in its production.
Mhm. So, here's some more specific, I guess, that obviously we went over that it needs to be no longer than 6 inches, and you want to minimize material because we learned how the ultimate goal is to use aluminum that is found on the moon to like 3D print these stakes. So obviously it needs to minimize material, but it needs to be strong enough to be used reliably. And we did some research onto the moon environment and how it can get very cold and very hot. It can fluctuate temperatures and there's dust and microgravity and all those things contribute to the harsh environment where it'll be even more difficult to create a design that can stand up to that.
And here are some of the constraints that are associated with the production. It needs to be lightweight but strong, not a tripping hazard. It needs to withstand the rough terrain of the moon and secure the equipment during these strong winds or unpredictable weather inclinations that may occur.
And also, hold on.
I'm sorry.
So, obviously, we did some research also into like astronaut mobility, and from your feedback, we also learned about how like astronauts, their chutes are pressurized, right? So when they're bending down or doing some certain movements, they might not have as much dexterity in like their hands or not be able to kneel down. So obviously, that has to play a big part into our design because it needs to actually be accessible for the astronauts. So this is our first prototype. Um, it we just focused on trying to get something like designed and developed and kind of the process of modeling and then printing. But we kind of figured out very quickly that this wasn't a very good like
Did it just break off at the top first?
yeah. So it broke off and we realized it was too thin and that for what we're trying to do, this type of coil isn't necessarily the best because it lacks strength.
And
So
then
how
we
did you
also
print that? Did you print it in the way that you've got it standing there? Or did you do it backward the other
So
direction?
we printed it like upside down to the way it's standing.
Okay, that sounds good. All right, show us the next one.
So this is our second prototype, so it's very different.
the second prototype, it just had like a better thread design, and it was like we used like a stronger infill, but like similar to the first design, like the we didn't have like a really profound like drill attachment. Like if this were to get drilled into like the surface of the moon, like I feel as if like it wouldn't be as effective because the drill attachment that's going to drill the tarp stake into the moon surface. Like if you look at the top of the prototype, like that circle in there, we didn't think that would be efficient enough to for the astronaut, not only with their limited dexterity in their hands to supply enough like grip to the drill to drill it in, but we felt as if the the drill attachment wouldn't be able to stay like fixated within the tarp stake in order to like efficiently
Okay.
drill it in.
So it looks like you have those threads are real tight. Is that correct?
Yeah.
Okay, it's hard for me to see it on your slides.
Yeah.
Okay.
So
all right. Did you make another attempt?
Before we made another attempt, we tried to kind of break down our design so far and how it can be improved. And some things we focused on were how obviously our drill attachment isn't ideal yet, but some feedback we got from our teacher, Mr. Lefter, is about like current drill bits. So one thing I have right here is like, um, so current drill bits would use like kind of a hex end to attach.
Sure.
So obviously we have like an indent kind of attachment here, but we're thinking for a future design, we could have the top of the drill and then a hex little
I
attachment
think that's a
sticking
good
out, which would
idea.
probably be more easier to use with any drill because it's obviously a hex standard. And also it would probably be more reliable. Um, and another thing we focused on was how obviously we pointed it to we made the drill stake come to a point, but our thread doesn't go all the way to the end of it. So since we're focused on making it as easy as possible to drill in, we're thinking since it's going to be drilled into a very hard surface, like similar to concrete, um, if the way we have it right now, it would be hard to like get the stake started drilling in because once you reach the thread, that thread is what helps it kind of
So
drill in. So
how much of a taper is that on the tip? Is that like a 45-degree angle or something?
yeah, so
So you could imagine if you just change that taper to something like you know, um, half of what you've got there, it would probably be a
yeah,
lot easier to get it in, wouldn't it?
yeah,
Okay.
and what you're saying about the kind of like the spacing of the thread is it's very tightly wound, I would say, when um we really want it to be driven in. So my like feeling so far is that um it doesn't have to be as I don't know tightly spaced thread because we want it to be driving it forward into the ground as much as possible, I would say.
Very good. Okay. You have
So
another version? Oh,
so
look at
this is
that.
our
That's
third
looking good.
prototype. Um so we haven't printed this one yet, but this is what we have so far. And obviously we're trying to incorporate the hex and the taper that we pointed out.
So now that hex is sticking up.
Yeah.
Do you want it sticking up so that we trip on it? Or would you rather it go inside so that we can avoid that?
Well, while we were designing using AutoCAD, we found some like difficulty trying to like extrude this hex into the tarp stake. So I align with what you're saying. I believe that it will be more beneficial to have that inside as opposed to having it outside to become a potential hazard to the astronauts. But one of my concerns with this design is that if we were to put the hex within the prototype in order to attach the drill attachment, the thing is like we mentioned this before, the astronauts have limited dexterity in their hands. So what's keeping the drill fixated in this thing so that their hands like we said before that they're not kneeling down, like they're crouching. So then if we can is there is this design gonna ensure that while we're drilling, like the drill attachment doesn't remove itself from the tarp stake? So that was one of our concerns.
Okay.
This is
Well, and part of the thing you should be thinking about is if you stepped on that with your shoe, how would it feel?
Yeah.
Yeah.
So, why did you choose to use a square on top?
Um so that kind of like being honest wasn't a part of our consideration. It's just kind of our choice, but I guess going further, um, we should be more mindful about like every single little choice because maybe a square obviously has like a bigger profile than a circle. So trying to minimize the tripping hazard, it would probably be a better choice to choose circular design or something that's more out of the way, I would say.
Sure. Now, and don't let me pull you away from that. If there's a
Uh-huh.
good reason to use for that head
Okay.
section to be a square, stick with it, right? I think that there can be some good reasons for using a rectangular piece on top. What's the second piece on the left of it there?
Okay, so we have with our design constraints, there's specifics for the type of grommet on the tarp that we want to use it with. So we have I'm pretty sure 1/2 inch grommet is our
Okay.
what we need to be testing with. So I guess what we have on the side is just for reference to make sure that the width of the actual stake is not too much.
Okay, I think that's a great idea. I like where you're going with this, guys. So were you able to did you put the last one into dirt or some lunar regolith simulant, or what did you guys do?
So do you want to explain the concrete?
So initially what we thought was that the tarp stake would be tested using like actual concrete like solution, like using like a water-based like solution
Well,
to like
yeah,
mix with
you don't want
concrete.
it wet. So this is going to be dry concrete.
Yeah.
We use concrete because it's got broken pieces in it, all of that powder. And before you start it, so if you've got it in a bucket, you want to pour it in there, and then you want to tap the side so that it kind of compacts. And then when you put your stake in there, it'll be more like what's on the moon, just because of that compaction is what's going to make a big difference. Does that make sense?
Yeah.
Okay.
So we have our prototypes so far, and we're gonna continue developing those, but we just got like all the testing materials. So we have like the concrete mix in the bucket. So we just need to take some time to get that set up so that we can really get going with each iteration and testing.
Excellent. Okay.
So you don't want to make solid concrete. You just use the powder, okay? Because I've had students think that they were making it into concrete, but you're not. You're just using the powder. But as Glenn said, pack it down, because that's the way the regolith will be on the moon.
Now, another thing you might do is see if you can increase the width of your threads. The more dirt that the threads are holding, the harder it is to pull it out. Does that make sense?
Yeah.
If we were to increase the width of our threads, do you think we would need we would like in our design, like if we increase the width of them rather than having multiple of them, like do you think we can utilize less threads in that way? Like instead of like you see how
Yes.
they're like tightly packed. If we were to increase the width of them, then essentially they would be doing the same job with like less material. So is that like a way we can conserve material in that sense as well?
Yes. Yeah, I think you want to decrease the number of threads per inch that you have, and that will probably help you with amount of dirt that you can hold, just because you can extend their length a little bit and have be able to hold more dirt that way.
And decrease your minor diameter.
Yeah.
Say that again.
Decrease the minor diameter, or the actual the
Yeah.
solid shaft size.
Yeah,
That's right. You don't need a big shaft. You need bigger threads.
Right.
Okay.
So how are you going to print this? In what direction?
So what we've printed so far has like a flat surface somewhere, so we could just print it on that. But this, we would need supports, I guess, and to remove those after. So,
we still have to take
yeah,
that into consideration.
so we have to take that into consideration, I guess.
Right. So I'll throw out an idea. I haven't thrown this out to anybody else yet. And that is, if you basically only had threads on opposite sides and you printed it to where it's laying down, then you would need a lot less support structure to print the threads. Is this making sense?
So
which would which would mean you would need an oblong top, right?
Mm-hmm.
Because you don't want a square, you want more of a rectangle or an oval type of thing.
Yeah.
But then that might be a little bit trickier trying to draw that.
Yeah. So you're saying using an like a oval, I guess, top, you could print it on that
Right.
face
So
and it
let's
would
say
minimize.
you look at this as four-sided,
Uh-huh.
right? And on two sides, you basically just completely shave all the threads off.
Okay.
And then you
Oh,
print it laying on its side. Does that make sense?
Yeah, I think I understand.
So then it would be printed this way. And then let's say that if we're looking at the tarp stake in terms of the threads, like let's say the side facing us and the side facing the back of the printer, those sides wouldn't be threaded as opposed to the top and the
Correct.
bottom. Okay.
Correct.
Mhm.
All right.
That's interesting because on Earth, we don't even think about that, right? But you're talking about printing something on the moon, and every ounce of that aluminum counts. And there is a cool way of actually eliminating. Do we need that other side? Is the question. And this project involves a lot of testing. You've got to print different things, different widths for the stuff that goes around, different widths for the centerpiece, and see which works the best. And take videos of when you're and actually Glenn says weigh your stake before you do any scaffolding and weigh your stake after you do any scaffolding, and take pictures of that too, because every ounce of that aluminum, if we can prevent it, that using it, that would be really cool. The one thing I don't understand about this project, Glenn, is are you expecting the astronauts to take their drill and drill into that flat square that they have? They added some height to it, but we don't want the height because it's a tripping hazard, right? But is the astronaut going to take his drill and put it into that little hole in the top?
No, the astronaut's going to take its socket driver or something.
Okay.
So that, let's say you have an inset that's a 3/8 inch, accepts a 3/8 inch socket, not socket, but the extension tool, right? That is the square and has that little ball detent which locks it in place.
Yeah.
So that I think that's what Glenn was kind of alluding to, is that this would be an inward versus an outy type of attachment. I also think at the top, what you're looking for is a nice radius top that goes to this either a 3/8 or 1/2 inch, however big this thing's going to be, recess thing, so that a socket extension will just lock right in.
Yeah.
Yeah,
because
that's right.
At right angles, you're going to get great torque.
Yeah. So basically, we have like the hex socket, but instead of being an extension, we want it to be like indented
inside. So like,
that's right.
Yeah.
And then I have a question. So addressing the height as Miss Flo just promoted. So if we were to reduce the height of our tarp stake, and let's say in testing, do you think it would be more beneficial in a sense that like if it would be more tightly drilled into the surface as opposed to like having that height? Because if it were to have that height, it's more susceptible to leaving the surface, right? Because then things can like the astronauts could kick it, or like if we said that the increments of the weather in the moon, like if it's more tightly wound to the surface as opposed to having that like space for like something that occur, like let's say corrosion or something other of the sorts, like do you think like having a shorter tarp stake is more effective in that way?
Well, I don't know. So right now we're telling everybody to make them all 6 inches long just because that makes it easy for us to test.
Okay.
The one when the astronaut, the ones that we print on the moon, for all I know, they might be 2 feet long, right? I don't think they will be, but they could be. Okay. And so here, by having really tight threads on there, I think that you're kind of mixing up all of the dirt that's right around your stake, and it's making it loose. But if you have a larger thread that is with more spacing, I think that as you drill it in, you're going to be leaving some of those layers that are still tight and packed from a billion years of packing, and it'll make it harder to pull it out. So part of what I think we're trying to get is a fairly large thread that cuts deeper into the dirt away from the central core of the thing. Does that make sense?
Yeah. So that reminds me of one thing we researched is like current kind of designs for similar products. So we researched like stakes and concrete screws
And like
and tent stakes. Yeah. So obviously tent stakes aren't screwed in, but they're still driven in. And one thing we noticed with concrete screws is how, like you said, like you pointed out earlier, there's not always thread all the way around. There's sometimes I don't know how to say it, like the
there's
thread
breaks in
on
the
opposite
thread,
ends
right?
and then no thread, and also it would have a very sharp and extended thread that's not very tightly wound. So I think concrete screws are a very good kind of analogy for what we're doing here.
Yeah, I think so too. Good job, guys.
Yeah. Thank you
Very
so
good.
much.
Thank
Yeah.
you.
And now I understand what the astronaut's going to do. It's not going to have to bend down. He can hook his stake to the drill, the thing on the drill, and then put it in the ground. So thank you, Stacy.
Good job, team. Keep this up.
Thank you. All right, you can always ask questions. Just copy your teacher on. Thank you so much for that presentation. Sorry. We got to move on to the next one because we got two more to do.
Hello, how's it going?
Okay.
We have two more. We're doing the same.
Well, this is
project.
another additive manufacturing one. And then we have a CubeSat heat.
I won't get into. Sorry.
Don't tell us your
I know, yeah, I won't get into that again.
Yeah.
So,
Thank you.
we're doing the NASA HUNCH, the Lunar Additive Manufacturing.
Right.
So, yeah, these are
Show us
all
your
the
snake.
things. So this was the first idea that we had. The idea was that we have a top handle, and we kind of had this idea of multifunctional purposes or multifunctional parts for our design. So we want to have a top handle that can attach to the top of the drill. And in addition to that, we also want a handle part, you can see over here, to also attach to that drill attachment. So we kind of screw on, and you kind of use that to plug it into the ground initially. And I thought a few benefits of this would be that it's easier to hold, it's an ergonomic design. So maybe in case you don't have a drill, you could just screw it in using this handle. And this also ties into our second idea, which was retractable stakes that would go into the ground for a better hold. So basically what we had was 3 layers of spikes, flat spikes that would attach at a hinge to a central screw. And what there would kind of be is, I know that based on this design we have here, it may not be, it's more something I have more in my head. It may not be the most clear with this, but it would be a cover that would be attached to the top handle. And basically, like, as you push down on the top handle, it would control whether the spikes were facing outward or facing inward. And then you could also twist it and it would kind of lock it into place. And there would be locking mechanisms. So you can control. So when you're putting it in the ground, the spikes would be up. So that's easy to put in the ground. And then you push down, and then this cover kind of moves the spikes so that they're at an angle where they're in the ground. And then it's going to be more difficult to pull it out. And then if you want to pull it out, you just pull back up on it, and then it kind of releases the spikes, and then it's easy to unscrew it and pull it out of the ground. So that was the main feature that we had for our design. And then you can see here the insertion, the leading pro and removing process. You know, when you pull it up, when you pull it up or you're putting it in the ground, spikes are out like that. And then when you're putting it in the ground, you push down and then it
So you would
covers.
hammer this thing down into the ground, and then you would turn something, and it pulled these flaps up.
No, you would it's controlled by the top handle here. So you'd push down on the top handle, and then all of these covers would kind of fold down over it, and then it would change the angle that the spikes are at. Oh, but we're still working on the design of, but that's the main idea. We want
Okay,
spikes
so
equal
does it
control.
screw down into the ground, and then
Yeah, it does.
you
It
and then
does.
you pull up, and it pulls the sleeves up, which pulls
Yeah,
the. Okay, I think you're
exactly.
going to need a mechanical advantage uh, to move those sleeves up,
hmm So what would that entail?
because, yeah, that's, well, it could be. Oh, let's see. It, well, it could be another thing that you rotate, a different thing that gets rotated, that
hmm
that that moves an inner body that pulls those sleeves up. But okay.
Mm.
So it looks like it's tapered uh from wide to narrow, from after the first point to the top of it. Is that correct?
Yeah.
Okay. So yeah, so it's a very fascinating thought.
So what do you think of, you think a design like this is worth the effort, I guess, or the
Oh,
complexity of going
absolutely,
into?
absolutely, absolutely. So I think there's two turning mechanisms that you need to think about here. One is you twist the entire thing down into the ground, and so you need to make sure that these wings are actually in a series, like they are, like a thread would be. Okay.
Okay.
And then once you're down there, then what you need to be able to do is you need to turn and maybe an inner screw, which
Right.
then pulls those sleeves up, and then puts force on these. So do you have, are these, is this a three-legged, four-legged, five-legged, these wings? How many
Right
per
now at the
sleeve?
moment we just had three, but
Okay.
after
And three's
testing we could
fine.
add, after
Three's
testing
fine,
we could see if three is good, if we need
right?
more. If,
You're yeah. So I think it's reasonable. Um it's kind of a neat concept. It's the thing about it is it's a little bit more time consuming, because you're
Mm.
screwing the thing down, and then you're activating it by
Yeah,
rotating another thing. So
yeah,
you have to have something that keeps it still while you rotate the other
right.
bolt that
You think I should
that
have
activates.
like
Right,
stabilizers on the side to keep it
right.
in place while you're
So your tool there
screwing it?
has to be the stabilizer, right? So your tool acts as a stabilizer with the, I don't know, you might put your stabilizer on it after you drill the thing down, and then you use a different size thing to grab a nut internal.
Yeah.
But it's a very unique idea. Very unique idea.
Is there anything on Earth that is like this?
Um, no, I didn't really base off of anything. I just, my teacher, Mr. Lefter, he's sitting over there. Great man. He kind of had this idea of spikes that go in and out, and then I kind of ran with it and wanted to implement some sort of thing where you have to be able to move the spikes depending on if you want it in the ground or if you want it to stay in the ground or if you want to take it out.
That is awesome. I like the creativity. That, you got challenges, like Stacy said. You got to figure things out. But I like the challenges, and make sure that it's not a tripping hazard. That's
Oh
real
yeah,
important.
that's why we included the detachable handle so
Yeah.
that you could
So
unscrew the
you need to
handle and
work
then
on your
say,
mechanism for making it all
yeah,
happen.
Yeah.
absolutely.
Okay, so do you have another prototype after that?
Oh no, that was what we've been
That's
working
it.
on. So you can see here, Amir, my partner, he's gonna read the benefits and trade-offs of a design like this that we came up with.
Yeah, so the benefits for this is that it would be really easy to use, like, because it's just a simple process with a few moving parts and steps. So and also enhanced stability. It has wide flat spikes which increase surface area for better anchoring in the ground. This leads to more resistance to pulling forces. It's also a reusable mechanism, can be reused over and over while maintaining the shape, the function, and its stability. The design could be used with or without the drill because of the handle, the detachable handle. Uh, and it can be used for all environments. Sturdiness and locking mechanisms means it can be used in like all sorts of environments. The trade-offs for this though is like for us to manufacture it would be like we have to spend a lot of time to uh like manufacture the actual thing because it's like we need to be precise with the things and there
Yeah.
might be failure and we just have to like keep on trying to till we like get perfected.
Yeah.
The since we're using like this mechanism like that's like not like simple, it might like the things we use are probably gonna be like a lot of weight, so it might make it like really heavy. We're gonna get to that after, and then maybe decrease the weight after, and then yeah,
And
This
then debris can accumulate within the actual mechanism, which can damage things. And also, there's a learning curve. It could take some time in order to get used to learning how to use it.
So this is the only, sorry.
So this looks because of the number of parts that have to be moving, it looks kind of complicated. Um, I think that it might be good to see if you can decrease the number of parts a little bit so that it's more buildable just within the time frame that you've got for school here.
Yeah.
I mean, if you can demonstrate two of those things coming open or something like that, that would be terrific. But having multiple of those, I think it'd be a lot.
Just like
Does that
one on
make
each
sense?
side? You think just one on each side? And
Yeah,
just try
just
to
one on
see if
each
we can get
side
there?
could give us an idea of
Okay.
how it would function, and that might make it easier for us to be able to make it just in that short period of time.
Yeah. Yes,
It's
thank you.
very unique, and you need to take the risk. That's the way things are developed. You got to take a risk to make new things. So I
Okay.
appreciate your design.
All
Yes,
right.
thank you. We'll take
Good
notes of that.
stuff.
We'll make it simple. We'll whip
Yeah.
up a prototype for you guys, and
Thank you.
it'll be great. All right,
Thank
thanks,
you.
guys.
You
Appreciate
have
it.
a
Thank
wonderful
you.
Thanks for your
afternoon.
time.
Yep. Keep it up.
You as well. Take care.
Very good.
Okay. So now we're moving into the Bergen County's Technical School with their CubeSat heat
Excellent.
transfer. And that's their last team. And then I see our Olympia team is on too, and they'll come after the with another. That's the only two heat transfers I have.
Okay, excellent. I think that's the Jonathan. Is that right?
For the
Oh, here they come.
yeah.
I'll just give us 1 second. Yes.
Yeah, that is. There's 5 kids on the heat transfer.
Oh, excellent. There's a lot
team.
to do on that one. So let's see
Yeah,
how they do.
yeah.
Megan knows. All right. Six skips.
We see it.
Yeah. Okay. Hi. So we're the CubeSat heat transfer team. We're composed of.
So my name's Alvin Dreyer. My name's Andy June. My name's Jonathan. My name's Max.
And my name's Sarvesh. So let's just quickly talk about the goal. So, satellite internal components also produce heat, just like electronics on Earth. So something key is that heat must be dissipated away from these internal components to cool it down. And something else that was important to consider is to also reflect external heat coming from the sun so that it doesn't heat up even more. So our solution has to add as little weight as possible, utilize as little power as possible to cool the satellite to keep it efficient. And we also need to dissipate the around 0.006 kilowatt hours of power coming from the fish tank heaters, which we're using as battery and processor.
So for the constraints, one of the main one that we have to consider is the fact that the whole satellite is going to be within a 10 centimeter by 10 centimeter by 20 centimeter rectangular prism. And along with that, the fact that the CubeSat's going to be in space means that there's going to be conditions of a vacuum. So that means there's going to be no possibility of convection. And so we have to utilize conduction and radiation. Some of the other constraints is the fact that the processor chip and the battery must be only showing one face, in which the processor is on the top and the battery is on the side. And also on the 10 centimeter and 10 centimeter side, there's going to be the antennas and the lens. And some of the other ones is the fact that there's going to be the sealed satellite. And within that, we're going to have to use the insulated bag to replicate the vacuum conditions.
All right, so moving on to the design. The most logical solution we found was to utilize a heat sink made of a highly conductive material to dissipate heat from the components into the walls of the satellite. Our initial design included a grid pattern to save on material and dissipate the heat faster in theory due to the increased surface area. This is something we'd like to test when the simulation is finalized, but for now I've left the grid pattern out of the currently modeled design. It's possible that the design without the grid will work better since more of the surface is in contact with the walls of the CubeSat. The prototypical heatsink design includes two copper sheets connected with small pipes. Thermal paste will be used to ensure good contact between the components, and insulating epoxy will be used to secure the heatsink. We're actively trying to find solutions including heat pipes, but this may be difficult due to the nuances of simulating heat pipes and space limitation. Heat pipes in a grid pattern could be effective. To deal with the sun's heat, we intend to use a reflective coating or film on the outside of the satellite. As Flo suggested, the most likely option is anodizing the aluminum on the outside.
So to adjust the constraint, the design that Jonathan went over is going to be using 101 copper, and it's going to be placed around in a grid-shaped format within the satellite, and that's going to be able to allow the heat to be transferred to a wider area of the CubeSat's outer shell for a higher surface area that the heat will be conducted, resulting in more efficient heat dissipation. However, the design will have some limitations because, for example, there's like the monetary, like money, like pricing constraint for us. So, but for NASA, for field testing and deployment purposes, we recommend using something more conductive but expensive like silver. And in addition to this design that Jonathan came up with for like the heat pipe and like heat sink combination, we were also thinking about using a multi-layer film design for the outside to adjust the sun's radiation. However, due to the thickness of the film, there's not going to be enough space between the launcher and the CubeSat, so we can't use the multi-layer design.
Yeah. I think okay. I'll speak briefly on our initial idea for multi-layer installation. So most multi-layer installation was is used on like larger satellites, and we would have used alternating layers of material that's reflective to the high IR waves coming from the sun, and the material emissive to the low IR waves coming from the satellite, which ensures that the heat radiates while in the space. But after discussing with Flo, we determined that there would be absolutely no available space in the CubeSat deployer, even for something as thin as layers of film. So the multi-layer solution is inapplicable to the problem. My concern for using something like anodized aluminum is that highly reflective surfaces are very bad at emitting heat. so the heat may be trapped inside the satellite, and I'm yet to find a solution to that if it even needs to be considered.
So one way that we started testing our solutions was using heat simulation software such as ANSYS. So for this, in this picture, you can see a model of just a regular Allen bolt. So, and you can see based on the color that shows the temperature of each part of the bolt. So then we decided to use this to try and simulate the temperature and the heat transfer in space. So this is an example. So you can see where the satellite is more blue. It has a colder temperature. So that's around, I think, -1 up to about this yellow part, which is around 10 degrees C. So this is with anodized aluminum and also with the heat from the sun. So this is with the walls removed, so you can see the inside, and this is with the walls. So you can see most of the heat, right? It's still concentrated in a smaller area because like right around, if you can see my mouse, under, I don't think they can, but for the
We
side
can.
that's, okay, yeah, right under the mouse, right under that wall is about where one of the heat sources is, and then around here is where the other heat source is. So it makes sense that around here would be where the greatest temperature would be. And then also, this is just of the heat sink. And you can see over time, this isn't over a very long time period, but you can see the heat from the sun moving across, and then also the heat this way from the processor, which it's connected to. And you can see that this heat from the sun is a lot greater, and that's probably more important for moving. Then this also shows the heat stress, where you can see the the heat flux. The heat flux is concentrated more around here, where there's the most heat coming from the processor. So for the next steps, we want to keep using this ANSYS software, and you can use this to test different materials. So we could use a different emissivity for a different material, and then also test other materials besides copper, such as maybe silver. And then also we want to eventually get a physical prototype and try and test our prototype in software physically. So yeah, thank you.
Okay. Very good, guys. I'm excited about the software you're using. I think that's really smart. Can you go up like 3 slides for me?
Yeah. So this, if you
Go
can
up.
see,
There you go. There's one. Now, hold on.
yeah.
So I don't see how your heat source is showing very much. Here I see the sun coming in, but I don't see your heat source.
I know. So our heat source would be, you can see there's a yellow part that spreads out from the center right where the mouse is.
Yeah.
So,
well, go up one more slide.
So this is just showing the outside.
Right, but shouldn't I see a hot spot right where the 2 heat sources are? There's no hot spot.
So there's a heat source in the corner.
Yeah, so if you look under here, there's a heat source here, and then I know there's another one under the heat sink, right? This flat side is
they're
the
still
top of the heat
blue.
sink.
I'm not understanding how it is that you've got a heat source there, but it's the same color as the rest of that whole plate.
Yeah, well, because we found that the heat from at least this isn't over a very long time scale, but the heat from the processor and from the battery was a lot smaller than the heat from the sun. So I think it was only without the heat from the sun, it only got up to about like 18 degrees C from 0 C in like about an hour.
Okay.
But I don't know. Also, the simulation is pretty
I expect the
preliminary.
sun to be a lot more, and that makes sense. But right here, I don't see any heat from it at all.
Yeah, I don't know. That might just be an error, but this is pretty
How much
preliminary.
heat do you have your heat sources producing?
Well, because they're 5 watts each, so I just have under here and then under this heat sink together is 10 watts total. But then in the simulation for the sun, I just put, I think it's like 1,130 something watts per meter squared.
That's right.
And then just put that as a heat flux over the entire outside.
Okay.
So, and then also there's radiation on the outside with an emissivity just around what aluminum has. So, I don't know, it still needs, the simulation probably needs to be tweaked more, but it gives a little bit of an idea of like how this is moving.
Okay. Well, what I'm suggesting is I think that you're because you're including the sun, you're not getting anything from your heat source, your two heat sources. And so do your same thing, your same simulation, but take away anything else and just see what happens with your two heat sources.
Yeah, I think I have pictures from the other simulation on another computer, which I could send, where it shows that after about, I think like 10 hours, this middle part right here gets to about 18 degrees C. But I need to work on that further.
Okay. Go down another slide. And don't think this is all criticism, and it's not. It's verification and making sure I understand what's going on. The fact that you guys have the software and that you're working with it tells me that you guys are doing terrific, because you're already understanding some of that software and how it's going to help you. So that's really cool. So have you guys picked up your fish tank warmers?
We haven't yet, but we're about to, because we're gonna do is like, as it says in the presentation, use some fish tank heaters, right? Just two 5-watt ones. And then if we can, we will try and use like a vacuum chamber, but if not, we might just use some sort of insulating bag. And then I think it says you can use a power meter to try and see if that correlates. If the power drop and the heat.
What kind of parameters do you get to put into this thing as far as environment into your model?
So one thing, let's see if I have a larger picture. Okay. Can I zoom in on this? Okay, great. If you see, you can add radiation, you can add like initial temperature. It automatically does conduction. And then also, if you see, I've left out convection. So that's intentional to try and simulate what it would be in space better than we could just doing the test physically, but with air. So you can add heat flux, you can add radiation, you can add, and I think it already does conduction. So that's very useful.
Okay.
And
okay.
You were
I think you guys are right on top of this. I think you guys are doing great stuff. So here's that meter that I was hoping you'd be able to find.
Yeah, that's what I was talking about.
And then here you can see I've got them taped kind of in similar locations. Does that make sense?
Yeah.
And what I found is, because of the texture on there, it does not conduct hardly at all to the aluminum. Does that make sense? So, yeah, as you guys are doing this exactly right with that software, I think that's going to make a huge difference in terms of what you guys can do with it. And I also think that as soon as you get your heat sources and you put it on something, you'll see how it does or does not conduct that heat very well. So keep this up, guys. I think you're doing good.
Yeah.
And Glenn, was I right to tell them that I was thinking of our CubeSat deployers, that they're deploying those CubeSats on the rails and you can't put padding around your CubeSat.
Yeah, so if you look at the
Yes.
spacing on there might be some room to be able to put some things in there. But I think people really try to avoid that just because they're trying to keep from getting a snag or something like that. They really want
Yeah.
it to deploy as evenly as possible.
Because we were thinking of using some sort of foil like Mylar, but then if it's sliding in and out, like that's pretty delicate, and then it might rip or, and that's not good. So I think it has to be something either very durable or like very thin.
So if you put the Mylar on the outside of that, would that be, yes, you're reflecting heat energy from the sun, but you're also keeping the other heat inside, aren't you?
That's why we were trying to use multi-layer to try and let some out while also let some of the heat out while also reflecting, which you can't really do with just one material, at least at the same wavelength. But then we don't think that works if we have a really tight tolerance for how much space we have. So then we might just end up doing anodization or something like that.
Well, and why'd you? And I have not looked up anodizing in terms of heat retention or reflection. What did you find out about anodizing?
Well, one thing is when it's anodized, it makes it more emissive, so that's better for the radiating outward. And then we thought since it's a metal, it might help. Even if you do absorb the sunlight, it'll conduct more throughout the surface. So we thought that would be better than having something just very insulating, and then that would just cause it to build up.
Well, the issue is that really any highly reflective surface we put on there will not be able to emit the heat as well. But I mean, since the sun is such a great concern, I think it's a trade-off that we'll have to make regardless.
Sure.
Yeah.
Well, and part of my question is about some of those reflective paints. How do those compare to the anodizing?
They're more effective, but I mean, a material's emissivity depends a lot on its surface qualities. That's what we found in the initial stages of our research. So even if it's just a very thin thing on the surface, like a paint, it'll greatly affect the emissivity. So we're just trying to figure out a solution so that balances both reflectivity and emissivity.
Because pretty much no matter what, if you just have one material, you can't be both emissive, right? Have radiate well and also reflective.
Agreed.
So then you kind of have to just choose which one is more important.
Understand. Okay. Well, I think it might be more difficult for you to do being able to anodize your parts might be a little bit more difficult than finding a paint. So these are just you're doing fine. You're weighing and questioning the right things. So keep this up, guys. I think you're doing great.
Yeah, and you can't anodize your part. We don't even anodize. We anodize a lot of our parts, but we send them out to be
and
anodized.
It's very expensive. So I don't want to.
Yeah, I mean that would be like a thing for NASA to do if they ever.
Right, you just tell NASA to do it.
Yeah, I think for our testing, then we wouldn't have been able to do any of that. So
no, don't worry about that. But you tell NASA, hey, they should do something.
Right, and that works.
Right.
Okay. Excellent job, team. Any other thoughts or questions?
That's it.
I think it's good.
So I want you all to be able to use that program, because you never know when somebody's going to be sick or whatever. You all need to use that program, and it's a wonderful skill. You're really doing a great job on using that. So make sure everyone on the team knows that. Okay. All right.
Job, guys.
Thank you. Thank you
Thank
so
you.
much.
Thank you.
You guys have a good afternoon. All right. So that was Bergen County Technical School, and I see Noelle there. She's their advisor, and what is your title, Noelle?
The district supervisor, math, comp sci, and engineering.
Yeah, and she's the one who got she's the one who got Bergen County involved by going to PCTI. So
excellent.
Yes, I actually met you guys at PCTI, but you probably don't recall. You probably met so many people that day.
Well, we appreciate it.
Thank you so much. Your feedback is super helpful to them, and
all right, you heading out then?
See them present.
Yeah.
Thank you so
Thank
much.
you.
Bye.
We'll
Thank you.
put this online too, so you can watch it later. All
Perfect.
right.
Thank you so much. Have a good one.
Thank you.
Thanks a
Thank you
lot,
for
Manuel.
joining us. All right. And so now we are going to zoom over to the state of Washington. Olympia, and this will be our last one for today. Hello,
Hey, Kate, how you doing? Good to
Olympia.
see you.
Hello.
Hey.
There are five of us, so there's a comically large number of us this time. So
Well,
sorry about
that
that.
is awesome.
It's gonna be a bit odd. But yeah, all right. So we're Olympia's heat transfer team. My name's Liam. I'm Evan. I'm Rod. And then this is Leo and Cruz over here. And let me actually go ahead and get some stuff up here so I can talk over it. So part of what we have gone through a lot of ideas for this originally, just with the original constraints of the size and the internal dimensions and the open space. We kind of have gone from considering some Peltier, some stuff involving the Peltier effect and some thermoelectric generators as kind of a heat recycler, or some more active cooling stuff. We considered sublimation cooling for a while, which is a lot of what Apollo used for the internal backpacks and stuff. And we're still maybe considering that for some other parts of this project as a whole, just because of how we kind of are going to need to do some stuff if we continue to go down the path that we're currently working on, which currently focuses on the idea of, let me just unhide a bunch of things here. Sorry about that. But currently, what our idea kind of revolves around is the possibility of extendable radiators that in the first part and when they launch, and the entire idea of this is we take some of the length off the CubeSat itself and put it into like an external module, like right here. This entire model still fits within the 10 by 10 by 20 centimeter cubed build area. And we have these hinges setups. We have a model of which here that we're still working on doing some fitment changes, and there's a couple things we need to adjust as far as tolerances. But the planned pretty concept revolves also around them being spring loaded and stuff. So when they're in the carrier themselves and when they're initially loaded, it's all retained kind of under its own tension and friction. And then after deployment, it transitions into having them deployed just without any mechanical, like physical, electromagnetic, mechanical parts, just spring tension, which works in zero gravity, which is a big plus. And we're also kind of working on right now, the current plan is to use heat pipes internally to route heat away from the internals out to the back plate, which we're probably either going to do out of billet aluminum or some other high temperature engineering material. There's a lot of additive manufacturing things, to some copper transfer surfaces on the back of it, that then when these hinges, which will have a rather limited range of motion originally, so when they're held down, they're going to be kind of flush and they'll stick up a bit. But we've kind of modeled it and put a lot of constraints on how far they can stick out and how far they can rotate. But once they're free to do what they're mechanically inclined to do, they'll rotate down to about 30 degrees off center from the surface of the CubeSat itself, and they'll make contact with the heat transfer plates and use heat pipes and some phase change materials that we're still kind of working on pitching tests for, to put stuff out into some copper or aluminum radiators. And yeah, that's kind of where we are right now as our main core concept for how we want to manage this.
Okay, I'm not quite sure. I see that you've got some levers that pull over, but I'm not sure I understand what part is extending out to give you more heat radiation.
So it is mostly
Oh, does this flip outward?
Yeah, I'm sorry that we don't have a physical a model to show you or move around for it.
Okay, so this one flips out in one direction, and then you have a second one that flips out on the opposite direction.
Yeah, so we have another one that flips out here, and then with I was working just off we were working, I should say, off the constraints that we had through the design, where the electronics and the batteries and all the internals come up to the very back edge of the other two sides. So we kind of worked around that, and we were just kind of planning on putting it on the two opposite sides on the outside. And by losing a little, we're We're planning on these being pretty thick, only 1 to 2 millimeters thick, with some reinforcement internally to compensate for that. And then having pockets in the externals that kind of allow for having them sit flush and not interfere at all with any of the conventional launcher setups.
Very good. That's interesting. I haven't seen that before. And so the idea that it's going to flip out and be perpendicular to the rest of the body, is that right?
Not entirely perpendicular, but it will have it'll have greater than 45 degrees separation from the rest of the body.
Okay. So hold on. All right. So here's my satellite.
Yeah.
And now I've put my heaters on the outside instead of the inside.
Mm-hmm.
And so part of the idea is, let's say this is the one. So you want to do this?
Pretty much, yeah. I think
okay. And then the other, now is it going to be on the same side as the heater or opposite side of the heater?
It'll be on the same side as the heater, because from my understanding, and please correct me if I'm wrong, from the design pictures we have or we received as kind of like the constraints for the internals and like where the heat was coming from, we wanted to take advantage of the empty space in between the edge of the electronics and the surface for heat management, and also because we're going to be taking not an insignificant amount of material off of the outside face of the CubeSat to kind of take advantage and set some more reinforcement and stuff to give it that full 3 or so millimeters of outside thickness back, but just do it internally at the sacrifice of space there. And we can work around that for heat management internally to get the heat out to where we want it to go to take advantage of the greater surface area for heat dissipation.
I think that's really interesting. That's a terrific idea. So using the heat pipes, you're going to go from the heaters to some kind of a panel that flips out. And by flipping it out, you're doubling its surface area exposure to the vacuum of space. Is that right?
That's the current plan.
And so you're hoping that you're going to be getting more emission because of that surface area that's exposed.
Yeah. And also, we've also given some thought to also using like some insulation and also some different ways. We're planning on doing some testing with paint and anodizing for like minimizing the amount of heat that can come in from the outside. Also possibly using the surface that the panel occupied as more heat dissipation by focusing more heat onto that portion of the exterior if we still want to take advantage of the shell itself in some way as a heat dissipation like surface.
Okay. I'm intrigued. I think you guys have some interesting ideas. Let's see. Be careful about the size of your levers that you have there, because so which side is the side that is toward the solar panels, is that right?
I believe so, yes, if I remember correctly, but that can definitely change as kind of
and that doesn't mean you can't do it. It just means you need to be aware of the other constraints that would be around there. And that's going to be hazy because we're not talking to those people.
Right.
Does it need to be as wide as what you see there? I mean, it looks like you've got it about 2 inches.
Thereabouts. It's let's see here. I forget if I worked this in metric or not. Nope, I did that in metric.
So it's about the panel is large, but the question I'm asking it is about the lever thing that you have on the top.
Yeah, okay.
Does it need to be that big?
No, not necessarily. We can definitely downsize it, and I think we're going to have to make some pretty big design decisions. Because as we've kind of looked towards it as like this design is like a jumping off point that we have here, we've also started to talk about how we want to move the heat through the levers, and we've like looked into some research, and it's like, yeah, heat pipes, because of how their wicking setup with the wick inside works, are a lot better than copper, but the struggle of kind of maintaining the structural integrity of this part and also incorporating a heat pipe into it is like something that we've had to like think about more as we've kind of approached this specific, like this review pretty much. So we're kind of debating, do we want to make them out of like something more like copper and mill them, or do we want to try and incorporate stuff? The big thing I've been working on recently is we've kind of taken the form of the outside of the hinge, and we were like, hey, maybe we can just like put the heat pipes on the outside. And so we have a bender template here. So if we heated the heat pipes up to get the copper malleable and just kind of squished it in there, We haven't done any testing on it yet. It's kind of a pie in the sky idea. Hey, maybe it'll work, maybe it won't. So I
Okay.
not
Let
lend
me just ask a slightly different question. So
Mhm.
before you were doing it like this.
It
What if
actually
you did
hinges the
this?
other way.
Ah,
Yeah, it
was it
hinges
going
the
the
other
opposite
way.
direction? Which
That
way were you
that
going to make it
latch
go?
keeps it that latch keeps it closed. Opening the
Ah,
latch
the
now
latch.
allows it to deploy, right? So the
The
hinge is
latch
in the
keeps it
middle of the
in.
box.
Now I'm with it.
Maybe.
Yeah.
So that latch could then be much smaller.
I would think about not using a latch at all. I would think about trying to use a metal that when it is heated, it has a memory bend in it, and then we'll deploy those panels 45 degrees.
So just use a spring action.
Well, it's actually kind of a memory, and which could be either activated by a current flow or by heat, so that and then so when it first gets warm, the first thing it's going to do is it's going to bend or straighten, and that would act as the deploying mechanism for these for these panels.
That's definitely an option. Thanks for pointing that out. I hadn't given much thought to shape memory of any sort. As just I haven't worked with it or don't have any experience with it. Originally,
Sure.
for like this, we had anticipated like the hinges being at the
Right.
top, but I do like the idea of changing where the hinges work and kind of working with something more like that. So we'll definitely add that to our list as far as options go.
Yeah.
Tell me. So I see that you've got it instead of being a rectangle, you've got it kind of shaved off on the corners. Why did you choose that?
We did that just as kind of a one, like a constraints thing, and two, so that we didn't have a whole lot. It was more of like a design interface thing, because originally we had planned up here for this to be like a hinge point for it. And
Oh, really? Okay.
yeah, but I do like your idea more of like the shape memory stuff and having it hinge from the bottom. I see a lot of options through that. Um, but it was more of just a contact thing to maximize the area that like was in contact with the thing originally, like so we didn't have a whole lot of the panel just sticking out, and also just to help it kind of keep its constraints around anything that also might be on this surface, whether it be the other hinge or anything else that just was on this surface in general, depending on if we want to move to the other side to make room for solar panels or something of that ilk.
Interesting. Okay, so wait a minute. Just another thought here. Most people are making their solar panels that they pop out just with a spring action. So they've got a spring on it, and as it slides out, the solar panels start deploying on their own. Okay. This has that same kind of style. It's just that it's panels of metal for dissipating the heat. I mean, there's lots of ways to make these things pop out on their own. Whether it's some kind of a heat memory metal or something, or even just a spring, could get these to pop out. And really, so it's really just the what do you call it? It's just the sliding out of the deployer, the friction between the friction of the deployer, of it coming out of the deployer, that makes it flip out. Does that make sense? I'm sorry, I garbled that all over.
I know it's fine, but that was like what we kind of thought. We were like, okay, if we want to do a deployable thing, it can't really have a whole lot. It's not worth putting a whole lot of extra weight for anything like a servo or like a linear actuator or anything to make it pop out on its own. So we did go into this with the concept of if we just make it want to go into the deployed state and we just hold it closed for the entire ride up, then there's no reason to really add anything else other
Sure.
than 5 grams of a spring or something like a shape memory
Right.
metal, anything else.
Yeah. I wouldn't worry too much about your weight, because you've got 2.6 kilograms. I haven't told you what the other parts of this are. So I don't worry about weight as much as worry about the functionality and how you're going to get all that heat dissipated. Okay.
All right.
Very nice, guys. I like this idea. I think there's something really exciting there.
Thank you.
Good job.
Yeah, I really like that you're just expanding the area for the radiators to give off the heat. You got to be a little careful because I'm thinking about the CubeSat deployers that we make at Hunch. They're one right next to each other with the ends. This top part. So it's one right next to each other, and they're you can't use up anybody else's space there.
Yeah.
So that Stacy's idea of some kind of thin metal that will bend is great. The hinge sticking out might be too much for it. Does that make sense?
Yeah, and currently right now the design takes advantage of, like, in the design itself, the back end where the solar panel end has an extra, I forget how many centimeters off the back of like the required electronics. And in this model, we haven't done that to this. This is the full 20, but we've taken all the space that we originally used for that, and it went into the space for the hinges being vertical in this specific rendering, I guess, of the idea.
So that's awesome.
Yes, this is still a 10 by 10 by 20 CubeSat when it's in the launcher. It'll be a bit shorter when it's out, but it still fits those constraints as a whole.
That is so cool. Yeah, I think you're really onto something here. Because if you look at the thermal control system on the ISS, we have radiators. We actually dissipate the heat using ammonia on the outside. We use water on the inside, but that ammonia is dangerous. So we have a heat exchanger. You might want to look into that. Years ago, Stacy, you had me looking into the thermal control system of the ISS. I don't know if you remember, but I spent a whole summer looking into that in summer. And so it's a very interesting way that they dissipate their heat using the radiators. You're just going to use a simple piece of metal for right now. But I like also that you're using those heat pipes because they look fantastic.
Hey, guys. So the rest of the body of the CubeSat is going to be aluminum. Is there any value to switching your plates to a different metal?
I think so. From what we're going to do some conductivity testing when we get closer to making like a full-on prototype for the heat testing and stuff. And I think we're going to steal a lot of ideas from the group that went before us and look into some dynamic computer simulation for it in both the deployed and condensed state for as many things as we can think to test with it. And
so,
then,
for example, the rest of it's aluminum, and aluminum is a very good conductor of heat. So it may be that you stay with aluminum, but having a couple of plates that are copper themselves might help out, or maybe there might be some types of steel that might be helpful as well.
Yeah,
so
we're going to look at
just some thoughts.
But yeah, we're going to look and we're going to do a bunch of testing on what radiates best before we make a final example and to show again in a few months.
Excellent. Okay.
Yeah, excellent job. Really interesting approach.
That's good.
All right, thank you. Thank you. Appreciate it.
All right.
Do you have any
Thanks,
questions for us?
You got one, Rowan?
Yeah.
Okay.
No, let me just get out of the way here.
Hello. The first thing I was looking into at the very beginning was like some internal heat pipe system. And I was wondering whether it would be easier to do maybe like a dual heat pipe system where there's just two heat pipes like parallel to each other, or like a larger one, maybe.
There's no reason to stick with just one heat pipe, and having a couple of parallel ones, I think, makes good sense. And it's just a matter of where do you want to spread that heat the most to, right? But no, if you've got an idea for a couple of parallel ones, I think that's a terrific idea.
Yeah, I was also looking into flattened heat pipes, like from laptops, something similar to that.
That'd be a good.
Yes, definitely.
And it would fit better.
Yeah.
Yeah. So the ones that I found on the internet were I think they were like about 4 inches long or something like that. And, but I know that you can buy some longer ones for just almost the same price. It might have been $10 instead of $9 or something like that. But I've also seen some students where they had like an old laptop, and they pulled out some of those heat pipes and they were able to use those as well. Okay.
Okay, thank you.
Excellent. Keep going.
Awesome. Any other questions?
I think that's it. Thank you guys very
Awesome.
much for your time. We really
Yeah, all right.
appreciate it.
Thank
Great
you
job,
so
Steve.
much.
You're welcome. Our pleasure.
And thank you, Stacy and Glenn, so much for joining us. I really
Oh,
appreciate
yes.
that. That was
You're
so
welcome.
awesome.
Okay.
All
We'll see you
right.
later.
So everybody enjoy their
Bye-bye.
afternoon. Have
You
a
guys
great
enjoy it
afternoon.
too. This
You
is getting into
too.
a drag.
Thank you so much. Bye-bye.
You guys. Bye. Bye.
Bye-bye.
How do I leave?
I'll